The kernel of a linear transformation is actually a set of all vectors that will actually come up with a zero vector on the codomain. Here we have two different linear transformations on R3 to R3, and we are going to solve here the kernel of a linear transformation. To do that, we just need to make sure that the equivalent value of the this side here, okay, and this side here will be equal to the zero vector representing R3. In short, we just need to find this values of this vector, which could give us this entire result be zero vector. So how do we solve this? Simply take out the linear transformation x, y, z. Okay, take note, we are going to solve for the value of x, y, and z here. That will actually make this zero vector. So this is equal to x, y, and 0. If we're going to make this equal to the zero vector in R3, x, y, 0 equal to the zero vector in R3, we can now get the representative values of our components of your original vector that makes it a zero vector. So this means that x is equal to 0 and y equal to 0. Notice the third is no longer a variable, so it stays as it is. That would mean the value of x and y that would come out with a zero vector in this given linear transformation are all 0. However, we don't know what z is because our vector here should be in R3. We have x, y, and z. And we cannot just simply say that z is equal to 0 because z here can take any value, because when you talk about the linear transformation, no matter with the value of z here, it will always be 0. Say for example, this is 1, 1, 1, 1, z, so 1, 1, 0, right? It always be equal to that. So 0 is just one of the possibility. In short, we can say that z can be an element of real number. Any real number could do here. Therefore, the value that we're looking for, or the vector that we're looking for, that will make zero vector here under this given linear transformation is the vector, okay, with components x being 0, y being 0, and z as any real number. And since the kernel of a linear transformation is a set denoted by ker of t, since this is a set, so let us try to come up with a set here, 0, 0, z, such that z is an element of a real number. This would be the kernel of the first linear transformation. So same thing here, let's duplicate the same process here on this side. Okay, let's just copy the given linear transformation, and we're going to solve for the values of x, y, and z that will make this zero vector. So we have z, y, and x. Let's take that z, y, and x and equate it to the zero vector on R3. Unlike the previous example, here we have exact values for x, y, and z. X is 0, y is 0, and z is 0. Or we'll start with z is 0, y is 0, x and 0. This would mean the vector here, okay, that will make this result be also equivalent to zero vector is the vector with components 0, 0, 0. And since the kernel of t is a set, we simply include here the set containing 0, 0, and 0. We don't have other values here because we have exact values for x, y, and z, unlike earlier where we treat the third component as z itself. So this is how you identify the kernel of a linear transformation. Thank you very much for watching.